Welcome everyone to this series of seminar in mathematics and high energy physics. Today we have Johanna Knapp from University of Melbourne. She did her PhD in Vienna University of Technology and then did several postdocs in Japan, in Calabi Institute, also in Max Planck. And I think we also did some visiting research at CERN. It's a great pleasure to have her with us today. Thanks for accepting the invitation.
Yeah, thank you very much for inviting me. I think this is a really nice initiative, and it's an honor to give a talk. So yes, I will give a whiteboard talk, and I don't think there's a lot of time pressure here, so feel free to interrupt me and just ask questions whenever you feel the need to interrupt. All right, so my topic is actually my title is actually a rather technical one called Gauged Linear Sigma Models and Calabi-Yaus. I just heard from Daniel that some of you may already know what Calabi-Yaus are. I will just sketch that, what they are in my opinion, which will not necessarily be the opinion of every mathematician. So here is the general outline and the plan of my talk. So what I want to do is I want to give a very long introduction, which does not necessarily have to do with gauged linear sigma models and Calabi-Yaus per se, but rather to give you the general concept of what is sometimes called physical mathematics, which is basically to use physics methods, mostly from quantum field theory and very often from using supersymmetry, to understand some concepts which have output into mostly pure mathematics, also in physics we hope, but also in pure mathematics. So this will be the first part of the talk, to sort of give a general idea on what we want to achieve with these gauged linear sigma models. And then I will say a little bit about Calabi-Yaus spaces, basically what I need to then come to the main part of the talk, which is to introduce at least part of this gauged linear sigma model and what it can do for us to study certain aspects of Calabi-Yaus spaces, so in particular Calabi-Yaus and their moduli spaces. And then, depending on how much time I have, I want to just sketch a few more recent developments. So part 3 of the talk will mostly be to give credit to a very fundamental result of Witten's in his original paper from 1993. In the last part of the talk, I just want to make a list of things that people have been working on in the past 10 years or so. If in case I don't make it, I will share my handwritten notes with Daniel, and then you can download sort of the list of topics from there. It's probably also incomplete. But the main goal for me today will be just to give you a basic idea on what the gauged linear sigma model is and what we can ask from it. And that should hopefully enable you, in case you are interested, to look further into it, to have sort of a background to read the current literature. All right, so let me get started with well, let's call it just physical mathematics. So many people call many things physical mathematics, so this is a very biased view. So for me, the general idea is to study topics that are of interest, hopefully, to physicists and mathematicians, but also in most cases, pure mathematics. Very often algebraic geometry, algebraic topology, enumerative geometry, something like that, using a physics approach. So it seems that physics understands mathematics very well, and we will make use of this. And I want to start with the rather basic examples or some basic features. So when I mean physics, in the context of this talk, and often more general, I mean at first quantum field theory. So I'll just along the way introduce quite a few acronyms that are hopefully rather standard, so that I don't have to do so much writing, and supersymmetry. So you won't really see any supersymmetry in my talk today, but it will always be lurking in the background, and it will be responsible for many of the structures that we will see, and also for many features of the gauge linear sigma model. So to be a bit more precise, what type of theories do I have in mind here? So what are the key properties of the theories that make an appearance in this kind of physical mathematics business? So very often, even though pretty much to every statement I'm saying in this section, there is an exception. So this is I should repeat that this is a very biased view. So very often these are field theories that are in low dimensions. So in this case, I will, well, by low dimensions, I mean less than 4. And in this talk in particular, we will look at a theory which is in 2 dimensions. So 1 + 1, 1 space, 1 time dimension. And usually we will make a big rotation to Euclidean space. So what the gauge linear sigma model is actually going to be is a quantum field theory with a lot of supersymmetry on a Riemann surface, which in string theory, in the string theory context, would be called the world sheet. So one thing is low dimensional theories. And another feature of these theories is also they are usually lots of symmetries. So in a sense, we make the theories very, very, well, comparatively simple. So again, in this talk, we will have a lot of supersymmetry, and usually this is denoted by n = 2, 2 supersymmetry. So for those people who haven't seen that, we have a QFT on a Riemann surface. We put complex coordinates on it that defines as a holomorphic and anti-holomorphic or left and right moving sector. And we have 2 supersymmetries in the left moving sector, and we have 2 supersymmetries in the right moving sector. And sometimes we have conformal symmetry, so scaling symmetry. But the GLSM itself will actually not be a conformal field theory, but we expect it to flow to a conformal field theory in the infrared. So a lot of supersymmetry. And when we have so much supersymmetry, there's actually, when you look at the symmetry group, you have the Poincare group extended by supersymmetry, but very often there is additional symmetry that just comes along the way. And in this context of 2, 2 theories, there are extra abelian symmetries. And I will talk about gauge theory, so I have to distinguish between global and local symmetry. So in this case, I mean a global U1 symmetry, or more than one, and this goes under the name R symmetry. So this will make a reappearance when I come to the actual definition of the GLSM. So this is actually induced by Susie. So if you look at 2, 2 theories, you get these U1R symmetries for free. So if I make the strong restrictions, let's say the actual physics, at least from the viewpoint of a physicist who wants to describe the real world, is not necessarily very interesting or realistic. So why? So one thing is when you're in very low dimension in particular, very often there are no or very few propagating degrees of freedom. So think about electrodynamics in 4 dimensions. The electromagnetic wave oscillates in transverse directions. If you only have 2 dimensions, there's just no directions left for a transversal wave. So there is a 2-dimensional electrodynamics will not have a propagating photon, and in that sense, it's not the best toy model for electromagnetism, of course. So, and the reason for that is, of course, it's highly constrained by the low dimension and also highly constrained by this, let's say, unrealistic amount of symmetry like supersymmetry. So nevertheless, there can still be some value to this low dimensional theory in the sense that it covers some aspects of the actual physics. So I don't want to say that these examples are just pure toy models for the mathematical physicist that have no value for actual real physics. So sometimes, irrespective of whether you want to study Calabi-Yaus with them or not, they can be toy models for aspects of higher dimensional theories. So for these 2D theories that I'm going to discuss today, they don't have propagating degrees of freedom, but if you add fermions, they're actually a toy model for confinement. So confinement is still something very mysterious in 4-dimensional theories. So these low-dimensional theories, in principle, can help with understanding aspects of the higher dimensional theories. So that will be not my main topic, but I felt the need to mention that there is actually also some interesting physics encoded in this rather mathematical area. Okay, so sort of the main point I want to make today is that the theories encode, well, at least hopefully, interesting mathematics. So how do they do that? So here I just want to list a few features of, how to extract mathematics using this like supersymmetric quantum field theoretic setting. So I think that the main point, which is not only true for the gauged linear sigma model, but also true for many other, sort of outcomes of string theory that have connections to pure mathematics, is that if you look at these supersymmetric theories with all their many fields and so on, the first thing you do when you study any quantum field theories, you want to find what the ground state is. And we're a little bit biased when we look at quantum field theories because we start off with scalar phi to the 4th theory, and that has a unique vacuum, and there is not really much to do. So many of these theories don't have that, and in particular, the theories that I want to consider today are theories where the vacua, or in other words, the ground states. And here I'm really talking about classical physics, so really classical vacua. They have a non-trivial geometry or topology. Yes, there is a question. Please speak up. Or not. Just interrupt me when you have questions.
Yeah, means by low dimension or by 2 degree, you means background is 2 dimension, huh? Because if you're talking about string theory itself, you require at least 26 degree or 10 degree to define the fermion or bosonic string theory.
Sorry, do I understand correctly that you're asking why I'm talking about 2 dimensions when I should have 10 or 26? I didn't hear properly.
No, I am saying by 2 dimension, you mean background, it's 2 dimension. Huh?
I mean that sort of the field theory itself is a two-dimensional field theory, and then I can have an embedding space which can be higher dimensional. So my action will be an integral over two variables, space and time, and not over like 4 or 10 variables. Okay, please ask again if I misunderstood your question. So the 2D, the field theory I'm going to consider, just to make that clear. So if I have an action like this, I have an integral d squared sigma, where these are coordinates on this two-dimensional Riemann surface. And how this Riemann surface is, the Riemann surface itself can be embedded into a higher dimensional space. And for instance, in string theory, the Polyakov action shows you how to do this. And what I'm considering is a variation thereof. Okay, I'm probably going to remove that again. All right. So yeah, if there are no further questions, just please shout out if you have more questions. I'll come back to the ground states. So the point I want to make today is that the ground states are not necessarily unique, but they can have an interesting, say, geometry and topology, or like any kind of interesting mathematics. And just to illustrate this in the most simple way with something that many of you may know is actually something that we will basically generalize in a very straightforward way. You can actually consider the Higgs field. So you take a complex scalar, phi of x. You can do that in any dimension. You don't need to be in 2. And you can just write down an action with a kinetic term and a potential. And then you may couple it to fermions and the whole standard model, but we don't even want to go that far. What's important in this case is that the ground state is determined by the zeros of the scalar of the potential, the interaction term in your action. And for the Higgs field, I will denote the potential by U, and I will only ever today discuss about potential interaction terms for scalar fields. You have some coupling constants G. This is a coupling. And then you have this famous fourth order potential. So you have phi is a complex field, so you have the modulus squared, and you have some parameter V, which if you do the theory of the Higgs field, you will actually know that this is related to the mass and the coupling. So for me, this will just be a constant. And this is the potential, and the ground state is just determined by the condition that we have a minimum. And if we draw the potential, I apologize for my drawing skills. We have phi here, we have u of phi here, minus v, and we have v, and then we have this famous thing here. And because we are in higher dimensions, this actually has a rotational symmetry. And then it's easy to see just from the picture what the ground state is. So that will just be a circle that goes around here. And that's what I mean. That circle is actually what I mean with non-trivial geometry and topology. We study a theory, we consider its ground state, and we find that the ground state is like a mathematical object. So we have that the phi vacuum is v times e to the I alpha. So it's a complex number describing a circle. So circle of radius v. Well, this is pretty much what we're going to do with the gauge linear sigma model. And I hope you remember this very simple discussion if I go into the technicalities of the GLSM. Because in the end, all we're going to do is we want to take an interesting theory and find the geometry, if you want, of the ground state. And So of course, if you wanted to study the mathematics of a circle, you wouldn't necessarily start off with the scalar field theory with the Higgs potential and then discover the circle as a new mathematical object by computing the series of the potential. However, when you're studying objects in algebraic geometry that are still present-day research, like Calabi-Yaus spaces, such an approach, which is completely analogous to what I've just shown you, might actually help you to find something new about, like, say, the geometry of Calabi-Yaus. So the basic idea of the GLSM is going to be take a complicated theory, supersymmetric theory, that where supersymmetry gives you a certain structure. Look at the ground states by finding the series of the scalar potential, and then find something that is more interesting than a circle. So this is the basic idea of, I think, what GLSMs were made for, to study Calabi-Yaus as ground states or as configurations of scalar fields as a ground state of a field theory. So this is basically the main message I wanted to convey in my talk.
Okay. Can I ask why they describe only from the ground state and no higher state? It is because you have only scalar fields, and these are sort of the color potential.
So let's say describing the ground state is sort of the first step. And the ground state will just, as we will see, give us, let's say, the Calabi-Yaus. But then you can go on and you can say, okay, what is my, you do what you do with the Higgs field. You turn on small fluctuations. You want to find out what sort of your low energy effective theory is. And you want to analyze the physics there. And so describing the ground state is only the first step, and it will already get you very far. But other than that, you can do much more. You can quantize the theory. You can solve equations of motion, as we will do a little bit today. They will not be as complicated because of the lack of dynamics. But in principle, you do everything that you would do with a quantum field theory. All right. But yeah, so finding the ground state is always the first step. And this is also what I want to emphasize. And it's not going to be as easy in the GLSM. All right, so basically the general rule is going to be that we consider more complicated quantum field theories, and usually they will be supersymmetric. Some of them will be conformal, which means that we don't just look at the scalars, we look at everything. So we add fermions, we have supersymmetry, so we have to. The gauge linear sigma model is called gauge for a reason. It's a gauge theory. So we add gauge fields, even though they are somewhat trivial in 2 dimensions. And so on and so forth. But general physics, namely Lorentz invariance, tells you that in any case, the ground states are determined by the scalars. So I will not go as far as to break Lorentz invariance. So my vacuum should be Lorentz invariance, and it tells me that basically the fermions and the gauge fields all have to be 0. And that's why I'm making such a big point about the scalar fields. And this is more or less all you're going to see in this talk. It's always the scalar fields, but you should always be aware that the theories I'm actually considering, if you're looking at the papers, they will have all the field content you want to have. So not gravity, it's not a gravitational theory, but scalars, gauge fields, and their superpartners. All right, good. So we will mostly focus that. The message is this: we will mostly focus on scalars in this talk, but all the other fields are there in principle. And if you go deeper, then they will also play a role. For instance, if you quantize and you want to determine the state space, you have to talk about, all the fields in the theory. All right, so this is one important point, that the vacua are important. And the other thing I want to mention for later on is that we have coupling constants. And physical theories, and this also goes a little bit back to this confinement toy model. Physical theories depend, or the theories behave differently at different couplings. That's very common. Yes, question.
Since you have taken scalar fields, so there will be no charge associated with scalar. So how will you
The audio is really bad. I cannot.
Are you able to hear me now?
Sorry, maybe you can type the question. I can read.
Yes, sorry. I think I'm not the only one with the problem. It's really the audio. Sorry.
It's really hard to.
All right, so I'll see the question pop up on chat, and I will stop and look at it once you're done. Yeah, sorry about that. All right, so I just want to say that the theories, not surprisingly, think about, confinement and running couplings. Theories, not low energy behavior of a theory, can very strongly depend on the value of the coupling constants or the parameters of the theory. And actually also the mathematics to describe, I will already call it different branches. Depending on different values of the coupling is different. So if you think about Calabi-Yaus, you usually think about algebraic geometry and geometry in general. But what I want to convince you in this talk with GLSMs is that you can go beyond sort of what's standard algebraic geometry by looking at the physics theory behind the Calabi-Yaus at different values of the coupling. So yes.
I want to ask, since you are taking with scalars, and there is no charge associated with scalars, isn't it?
Sorry, did anyone else?
No, it's not possible. It's not work. Please write the question.
Or can you? It was very loud now. Can you move a little bit away from the microphone, maybe? Yeah, I'm sorry. I'll go on for now, and we can try later. All right. So the point I want to make here, and this is also one of the messages I want to convey when I actually talk about the GLSM, is that there is well, some connections and correspondences linking different areas of mathematics. So the physics behind this is you have one theory and you have a parameter space. And at some value of the parameter space, you have one type of vacuum. And at some value of the parameter space, you have a different type of vacuum. And the mathematics to understand the vacuum is not necessarily algebraic geometry or topology. It could also be something like singularity theory, or it could be symplectic geometry versus complex geometry, something like that. All right, so basically in this talk, I want to show how these concepts I just introduced or sketched work out in a specific theory, which is the gauge linear sigma models. And I want to give a field theoretic construction of Calabi-Yaus spaces that, as many of you may know, play a rather central role in string compactifications as the 6 extra dimensions that preserve supersymmetry in 4 dimensions and are generally very nice mathematical objects to study. So before I come to this, so this was the physics part of what we're going to see, and now comes the mathematics part of what we want to see. Is I want to give some aspects about Calabi-Yaus. So I heard that some of the students here have been through a course that I would have been happy to have attended as a student myself. So I will not go into the details of complex geometry or Kähler manifolds, also because it will not really be necessary for the talk. But I want to focus on those statements which will reappear in the context of GLSM. So the first thing we need to, or some of you may already know, is what is a Calabi-Yaus? And my answer to this question is it depends on who you ask. So I think the most conservative and least controversial definition of a Calabi-Yaus is that it is a smooth, compact Kähler manifold. I like to call my Calabi-Yaus X, so here's some notation with, and then it depends on your preferences, and actually to understand the equivalences between these things is non-trivial mathematics. So one thing is with vanishing Ricci tensor, which is usually not very helpful because for like non-trivial Calabi-Yaus, the metric is not really known, so you cannot just go and compute the Ricci tensor. You may rather check if the first Chern class vanishes. Or, and I think that was actually the idea when Calabi-Yaus were introduced in physics, people were looking at string compactification in a heterotic context, and they wanted to preserve supersymmetry in 4 dimensions, which gave constraints on spinors. If you look at this, you will actually find that the holonomy group associated to Calabi-Yaus has to be of a specific type. And it has to be, if I remember correctly, if you count complex dimensions of Calabi-Yaus, it should have SU dim complex of the Calabi-Yaus. So for Calabi-Yaus 3-folds, it will be SO3 holonomy. All right, so I will not introduce what Kähler or complex manifolds are. You can look that up in Nakahara or your favorite textbooks. Maybe just to mention that Kähler means that the metric, so it's a complex manifold, so we always have holomorphic and anti-holomorphic coordinates, essentially can be deduced as derivative, as a double derivative of a potential, which is called the Kähler potential, where in this case set k, let's set bar k are the coordinates. Describing x. So yeah, so this is one definition, and I've already made a few put on a few constraints here that, especially in a physics context, when we talk about Calabi-Yaus, are relaxed, and this is the smooth and the compact. Even though it will not play much of a role in the rest of the talk, is that there are also non-compact Calabi-Yaus. So just in case you're seeing something like this, because often GLSMs also have this as a toy model, you can take 2-dimensional complex projective space. I should also say whenever I write P2, I mean complex P2 because everything's in the complex world. And if you know a little bit about fiber bundles, you can take a line bundle O-3 and fiber this over P2 and take the total space. This is actually also Calabi-Yaus and goes under the name local P2. So this is just a side remark. So I want to go a little bit further. So also, for instance, in the context of F-theories, Calabi-Yaus, which have some sort of singularities, are of interest. So also singular. But of course, when you are in the region where there are singularities, many tools of algebraic geometry don't work anymore. So all of this can appear in the context of GLSM, and sort of my physics definition of a Calabi-Yaus is something that has nothing to do with geometry at all, and that naturally comes out of string theory. And that is, it makes sense to take an n equals 2,2 super conformal field theory in 2 dimensions with a central charge So we have a left and a right moving sector of this conformal field theory. So we have a left and right central charge, and we take 3 times the complex dimension of the Calabi-Yaus. So this is like a worldsheet perspective on what a Calabi-Yaus is. And it's a very specific supersymmetric conformal field theory. And the point I want to make is that at least from a physics perspective, and we will see this in the GLSM, one can call things Calabi-Yaus that are not necessarily geometric. And that's what I meant with my previous remark, that somewhere in the parameter space of a field theory that has a Calabi-Yaus as a vacuum could be another locus, which still in some sense is Calabi-Yaus, but does not really have to do with geometry. And what I have in mind is something that's called the Landau-Ginzburg model, which in the mathematical world is related to singularity theory rather than algebraic geometry. All right. So this is about, various levels of definition of what a Calabi-Yaus can be. Okay, and the other key feature that I need about Calabi-Yaus is that Calabi-Yaus do not come on their own. They come in families parameterized in terms of moduli. All right, yes, question.
Are you gonna talk about N22 supersymmetric CFT?
Can I talk about, or will I talk about?
My question, are you going to talk about it?
Not really.
Okay.
If
it's not, can you questions like about the structure of this supersymmetric CFT is like you have two Grassmannian, right? Variables. It's correct?
Yes.
Or 4?
You have 2 left moving ones and 2 right moving ones.
So you, okay, right.
So you have 4 supercharges.
Exactly. And what about the generator of this N22? It's like you have like, can you just explain a little bit about this?
Yes, I can actually, I think I have enough material. So I really wanted to avoid writing down actions because most of what I want to say is about scalar fields. So what you can imagine is for this. So what I have in mind with these 2,2 superconformal field theories is, for instance, something called a nonlinear sigma model. So, so 2D non-linear sigma model. So the action is basically, well, again, let me use complex coordinates. It's an integral over the Riemann surface. And then you have a standard scalar potential term plus some further interaction terms. So you have superfields, you have chiral superfields that that contain well, a chiral multiplet, so a scalar field plus its fermionic superpartners. And you have basically a scalar kinetic term. You have fermion kinetic terms. And then you have this is just an example. You have a 4 fermion term, which actually is contracted with the Riemann tensor. So basically for the scalars, you have the theory itself is a map from the Riemann surface into a target space, which I call X for a reason. It's Calabi-Yaus, and the scalar fields are coordinates on X, and X is a Kähler manifold. So this actually has a Kähler potential in the fermion term, in the scalar term. And you really do field theory in the sense that you analyze the theory and you find that there are 4 independent supersymmetries. So you really have something like a Q, which is, it's usually a superpartner Q minus plus epsilon minus Q plus, this should be a minus, and then epsilon Q goes to epsilon bar, Q bar for left and right moving, and plus and minus labels the different supersymmetries. So you find that this action, which you can look up, for instance, in Witten's papers from the early 90s, has this supersymmetry, and the supersymmetry generators, they're really just, you use Noether's theorem, and you can express the supercharges in terms of, the fields of the theory. So this is as explicit as it gets. And in addition, it also has a conformal symmetry. So you can just from the action deduce the full superconformal algebra. So you also have like Virasoro generators and an energy momentum tensor that you can write down in terms of the fields. Does that somehow make sense?
Correct. Just one more question. So you say that there is Virasoro. So what other type of generator you have beside the Virasoro generator? I mean, for example, in the case of n equals to 1, you have these fermionic generators, but this is here you have, I think, something else more like.
So you have in each sector, so you have 2, 2, so you have the holomorphic and the anti-holomorphic sector. So you have a T of Z, which is the energy momentum tensor, and then you have Q plus and minus, which are the 2 supersymmetry generator. And then you have a further U1 current, which is associated to the R symmetry I mentioned before. And you have 1 copy in the holomorphic sector and 1 copy in the anti-holomorphic sector. And you can, if you take, for instance, the nonlinear sigma model, you can compute these things explicitly in terms of the fields.
Thank you.
Okay. Yeah, happy to answer this kind of questions. I'd rather have a discussion than go ahead. So yeah, so this is basically what I'm not going to tell you in this talk, because I'm going to zoom in on the scalar fields and the vacua, and I want to find the Calabi-Yaus. But I'm happy to at least sketch, even though I cannot give the technical details more about this, supersymmetric theories.
Yeah, don't worry. I think Professor Sunil Mukhi will talk about these Lagrangians and also this Landau-Ginzburg model. Yes.
So I should also say, because Landau-Ginzburg models are mentioned, a Landau-Ginzburg model will not be a conformal field theory, but there are conjectures that are partially proven in mathematics that it has sort of an infrared fixed point that is also a conformal field theory. So sometimes you can really write for the nonlinear sigma model that I just told you that will also play a role later. You can actually write down an action and check for yourself that it's conformal and computes the energy momentum tensor and everything. And sometimes you have a theory that you know has a conformal fixed point, but it's not conformal itself. And this is also what the gauge linear sigma model is going to be. The gauge linear sigma model will be a supersymmetric field theories where you have this, but you don't have the various orthogonal traits, not the conformal field theory. But we will see actually that the nonlinear sigma model can make an appearance somewhere in the infrared of the GLSM. And that will be, I will come back to that when I make it there. All right, so yeah, after this, I should just, this is just the intermezzo. And let's come back, and I just want to mention a few things about moduli of Calabi-Yaus before I move on to the actual field theory. So I will now assume that the complex dimension of the Calabi-Yaus is 3, which is what string theorists like to look at. And in the case when we have Calabi-Yaus threefolds, well, also for other Calabi-Yaus, but these in particular, it's very simple. You have two types of moduli. You have the Kähler moduli, which roughly speaking are the volume parameters. Remember the circle in the Higgs mechanism that had a radius, so think about things like that, complexified. And here's the relation to mathematics. How many Kähler moduli Calabi-Yaus has is actually related to the topology of the Calabi-Yaus, and what you need to compute to find out how many Kähler moduli Calabi-Yaus has is you have to compute a specific Hodge number. And actually, the moduli that will be relevant for today's talk are the Kähler moduli. And well, there would be mirror symmetry to relate this to the other type of moduli, structure moduli. So roughly the complex structure moduli like the shape parameters. Meaning basically that when you have a complicated enough topology, you have more than one way of deciding what is holomorphic and anti-holomorphic. And this is the Hodge number. H21. And for Calabi-Yaus threefolds, this is all there is because all the other Hodge numbers are canonically either 1 or 0. So this is actually the main content the main information about the topology of the Calabi-Yaus. So let me just mention a few examples. And actually, let me mention the example because this is what I want to reproduce in the GLSM. And that's the quintic in P4. So yeah, this will reappear in a field theoretic context. So how to describe the quintic? Let's start off with 5 coordinates x1 to x5 in 5-dimensional complex space. And at first we have to define P4, so it's complex P4. So again, I omit the C, defined. So there are many ways to look at projective spaces. I will use the standard way that is used in what's called toric geometry. You take some complex space of a certain dimension and you remove certain loci in this complex space. So in my case, what I want to remove is the origin. And then it's projective space. So there are some equivalence or scaling relations. So in case for the quintic, you say that x1, or less, actually it's the same scaling relation for all the x's is equivalent to lambda. And then you could have some non-trivial exponent there, then you would call it weighted projective space, but you're not doing this. So I just have a lambda to the 1. And this one will also make a reappearance in the GLSM, where the lambda is a complex torus action. So you have complex space, you exclude some locus in there, and you impose some equivalence relations or scaling relations for the coordinates. And this readily generalizes to the definition of what's called a toric variety, where you can have more than one scaling relation, you can have different weights in the scaling relation, you can have more complicated sets that you remove for the complex projective space from the complex space, like not just the origin. So it generalizes to toric varieties. All right, so this is P4, we call this the ambient space. So the last step we have to do is we take a generic homogeneous degree 5 polynomial. I will call it G5 of x1 to x5. This will also make a reappearance in the GLSM. So what I mean is that G5 is like lambda to the 1 and is homogeneous with respect to the scaling relation up here. So it's x1 to the 5 plus, I don't know, lambda 2, x1 to the 4, x2 plus ... And then you can, if I'm boring you with my trivial talk, you can convince yourself that you can go all the way to lambda to the 126 and have like x5 to the 5 here if you do the systematics right. And the Calabi-Yaus, the quintic, which I will call x5, is given by the hypersurface sets this described by setting this polynomial to 0 inside this space, weighted inside this 4-dimensional projective space. And there is a lot of different machinery, for instance, combinatoric of lattice polytopes and so on, that can tell you that it only has one volume parameter. It's because the ambient space is really simple. It's just a generalization of a sphere, basically. And H21 is 101. Which actually has a relation to the fact that we have 126 monomials here modulo some linear field redefinitions or coordinate transformations. All right, and this is the most famous example, and it will be the main sort of example of the rest of the talk. I should just say that this is not the only example of a Calabi-Yaus, so there are further Calabi-Yaus hypersurfaces. These generalizations of projective spaces in toric ambient spaces. So generalizations of this concept, complex space minus something modulo some relations. And I have to say this because this actually has been classified like 4-dimensional complex 4-dimensional toric spaces, and one complex equation in there gives something 3-dimensional, and that was classified by my PhD advisor Max Kreutzer together with Harald Skake. And they classified something called reflexive lattice polytopes in 4 dimensions, and each of these polytopes gives you a Calabi-Yaus hypersurface of the type of the quintic, basically, with more moduli and all this kind of stuff. And I really like this number. They found 473,800,776 of them with all the mirror symmetry in place. So there is an abundance of examples of Calabi-Yaus, and people only look at the quintic because it's the most famous one, but it's certainly there's more to do. And in principle, each of these examples can be realized in terms of a gauge linear sigma model if you work hard enough. All right, I should also say that there are more complicated constructions like complete intersection Calabi-Yaus in higher dimensional spaces, which have not been classified. And more recently, about something that I cannot talk about is also Calabi-Yaus that are not related to this kind of structure of a toric geometry. And in this case, so instead you're looking at Grassmannians or flag manifolds or something like this. And in this case, the gauge linear sigma model has actually been one way of finding new types of constructions of Calabi-Yaus. All right, yeah, any questions about this? Because now for the remaining 50 minutes, I want to sort of repackage all the information I've given you now in the context of the gauge linear sigma model. Okay, if there are no questions, then I'll just go on. Let me just start off with the disclaimer. That the GLSMs are not necessarily related. Yes. Sorry, the audio hasn't gotten better. Can you type the questions? I don't see anything on the chat window, I'm sorry. Okay, I hope I can somehow hear or read your questions at some point. For now, I'll just go on. So yeah, I just want to say that GLSMs are not necessarily related to Calabi-Yaus. You can also relate them to different manifolds. It's just my very biased view. And I should also say, if you want to read one paper on GLSMs, it's of course a paper by Witten, who invented it. In 1993, 93001-042. So the GLSM recently had its 30th birthday, and actually I just come back from a birthday conference at the Simons Center that happened 2 weeks ago, where we celebrated 30 years of GLSMs. All right, so I can really recommend these papers, like all of Witten's papers, they're just great. And they also will give you all the actions and all the physics and all the supersymmetry that I'm not talking about.
Is this the phase of N2?
Yes, thank you.
Okay,
Phase.
okay.
N equals 2 and then theories blah. Yeah, Witten has written so many good papers in 93 that one has to be very specific. All right. So yeah, my plan is to construct Calabi-Yaus. Maybe let's write it down. Well, let's say, well, actually the quintic for today as a vacuum of a 2D 2,2 SUSY gauge theory, which is the GLSM by definition. And what I also want to do is I want to explore the Kähler moduli space. And why this is possible is actually that there is a GLSM coupling for many of them, which are called the Fi theta parameters. So if you really write down the pages of action, pages it takes to write down the action, you have coupling parameters in front of the different terms. And there is actually a one-to-one correspondence, at least in the simplest example, to the Kähler moduli. So you have some field theoretic tools to study theories at different couplings and to study the low energy effective theories depending on the value of the coupling. And in the Calabi-Yaus language, that means that you're at different loci of the Kähler moduli space. And it's called the stringy Kähler moduli space because it actually has sort of an analytic continuation away from the volume parameters to values which you would not associate to a volume naively, like a negative radius, for instance. And that will make the connection between the geometry and the non-geometry. All right. Good. So now comes the technical part. And I'm going to introduce the GLSM in a way it's often done in the papers today and also in the mathematics paper. So the GLSM has been really been adopted by the mathematicians, and the language that's used in the papers today is not really the language that's used in field theory in the 90s in Witten's paper. So I already said that the GLSM will have a lot of fields, namely the scalars, the fermions, and the gauge fields, as I just sketched with the nonlinear sigma model. So if I scroll back to my little detour, in addition to scalars and fermions, we will also have gauge fields and their superpowers. And we will have different types of scalars, but morally it's the same thing. The action is an integral over a Riemann surface and a two-dimensional field theory, and it will have the same amount of supersymmetry, and you can also explicitly compute using the Noether theorem, the supercharges and so on. What you will not find is conformal symmetry. So I will skip all that and just give sort of the information that's relevant to analyze the ground states. And actually, when you look at the mathematics papers defining the GLSM, you will actually find that this is the only thing they give. All right, so what do we need? We need a gauge group. So there will be a compact Lie group. In most cases, U1 to some power that gives you all the toric geometry, or U2 or something like that. So it can be abelian or non-abelian, but the non-abelian case is still actually active research. So non-abelian GLSMs are still quite a bit of a mystery, even though it's only two-dimensional. And then I will introduce a complex vector space. Why do I do this? This is just really, that's going to be our manifold. So we will have coordinates. For now, I will call them phi I. And I haven't really fixed the dimension of my complex vector space. So this will be our scalar fields, or rather the scalar components of, for those who know supersymmetry, of the chiral multiplet. So you will have also fermions coming with these scalars, and you will have an auxiliary field usually called F, and I'm not introducing them. And the mathematicians will just say it's a complex coordinate, but secretly, of course, they depend on the worldsheet. So they're functions of the worldsheet coordinates of the Riemann surface. And mathematicians like to sweep that under the rug because they only look at the ground state, so they don't actually know that the phi i's are actually, if you're serious about these sections of some bundles over this Riemann surface. And you will see that we will actually get away with this. So because we have a gauge symmetry, our fields will of course transform under this gauge symmetry, and that's part of the data. So we will need to know how to how the fields transform. And also in a rather abstract mathematical language, this means giving a matter representation, which I will denote by rho. So this is the matter representation. So this tells us how our phi I transforms, and because they come in multiplets with fermions, and we know the properties of fermions, we also know how the fermions transform under this gauge symmetry, so we don't need this. So this is a representation, and actually I will introduce now my first constraint. So impose a restriction on this representation. And we just say that it's not the most general linear transformations on our vector space, but it's actually special linear, so determinant one transformations of this vector space. And this is actually highly non-trivially related to the Calabi-Yaus condition. And the reason for that is, if you look at the field theoretic context, you have these U1 symmetries, those that I have denoted by J here. And you have a left moving and a right moving U1 symmetry. And they are global symmetries, but they can be anomalous. And in particular, there are like two combinations of this left and right moving U1 symmetry that are called the vector and the axial U1 symmetry. And if you do your index theory, which I'm not really good at, you will actually see that the theory itself can have an axial anomaly. So it means that if you try to quantize it, you will find an anomalous, your symmetry will not be a symmetry at the quantum level. And to cancel this axial anomaly, you get a restriction on how the fields have to transform. And that is actually in one-to-one correspondence with the Calabi-Yaus condition, and can be traced back to sort of the vanishing of the first germ class. So this is how you should interpret this restriction. And I will be more concrete in the example what this looks like. So I already said we have this U1 left and right R symmetries. And you can take positive and negative linear combinations. And for the sake of this talk, I will only have like a vector U1, which is, well, it's really bad notation to write sum of U1L plus U1R, just mean you add up the weights, take the positive linear combinations. There's also the axial one, which is related to this anomaly here. So this is the vector U1. All right, and that also comes with the representation. So our fields or fields don't only transform under the gauge symmetry, they also transform under the R symmetry. And that's another piece of data we need to impose. We need to know what the R charges of each field is. So there is a representation, which I will also denote by R, and it's U1V into GLV. You also have the axial thing, but I will not mention this today. And because the U1s are easy, the weights of this representation I will call Ri. So these are the R charges of phi I. So we only have a bunch of scalars and we have gauge charges and R charges. So not much has happened yet. So I want to be a little bit more specific on the definition of the gauge charges. So what I will choose, because I assume that G can also be non-abelian, I will choose a maximally commuting subgroup inside my gauge group. So the maximal number of U1 subgroups that we have in there, that's called the maximal torus. Of G. And you have the associated Lie algebras. And actually, if you're a mathematician and you want to understand what the gauge charge is, you really have to introduce all this formalism here. And then the gauge charges QIA, they live in the dual of the complexified Lie algebra of this maximally commuting subgroup. So for physicists, gauge charges. So this index A here goes from 1 to rank G. So this is the most general things. So these are the gauge charges. All right, and then I kept talking about parameter spaces. So something that if you look at witness paper, you will see as part of the action is that there is a complex parameter, and this T here is not the same T as the Lie algebra. So I hope there is not too much confusion here. This lives in the dual of the complexified Lie algebra. So it's a complex parameter, and this is called this Faye-Ilopoulos or Fi theta parameters. So think about them as a certain coupling constants. It's a gauge theory, so you will have like the standard gauge coupling like the electric charge, but you also have this additional coupling constant that basically comes from the structure of supersymmetry. And they are complex parameters, and I will write them as, so they get an index A because you have as many as the dimension of the Lie algebras. So if you only have U1, you only have one. And because they're complex, you can write this in terms of a real and imaginary part. So the real part is called the Fi parameter. And this part, and again, this is sort of encoded periodic, is called a theta angle because for the theory to be consistent, this has to be 2 pi periodic. So, and these parameters, they are the coordinates on the Kähler moduli space of the Calabi-Yaus we have yet to construct. All right. So just for completeness, but for lack of time, I will just mention that there are also other scalar fields, GC, which are, because we have a gauge theory, we also have vector fields. And if you have a supersymmetric gauge series, the vector field comes in a gauge multiplet. And the gauge multiplet also has fermions and scalars. So these are the scalar components of the vector multiplet. Another type of scalars, and they naturally live in the Lie algebra of the gauge group, just like also the field strength tensor does. So you can write this as sigma is like sigma A and then the generators of the Lie algebra. So you do this, you do the same thing. And just for a bit of notation, you have the Lie algebra and its dual floating around here. And whenever you have a spacer and a dual, you can define a pairing that gets you a scalar product. So you have a natural pairing. Like this. And I will denote quite a few things with that. So in particular, you can naturally pair the Q's with the sigmas, which is like QIA sigma A. And sometimes I will write this as Q of sigma. So it's just, and similarly, we will also need that T sigma, which is TA sigma A. I will write it like this. All right, so far we just have fields and symmetries and how things transform, and we have parameters. So the next thing we need is a little bit of interactions. So we have an interaction term, in particular a holomorphic function of the phi, or actually of the superfields, which then again we focus on the scalar component. So this is I will call this the GLSM superpotential. And it's really superpotential in the sense that you would have the full chiral fields, chiral multiplets in here. But again, I will only look at the scalar part of this. So that's why I use the same notation. And this has to be gauge invariant. So you have that W of, well, there's a gauge transformation. Where in this case, this is not the Lie algebra, but the group element is W of phi, that's invariance, and it has U1V charge non-zero, And the standard convention is to have two. So we have W, we have a U1 action on the of the R symmetry acting on the fields, and this has to have weight 2. And this is already where you can see that this cannot be a conformal symmetry, because you have like a potential that introduces an interaction term that introducing is a non-trivial scaling. So this theory cannot be scale invariant, and therefore we don't have a conformal field theory. All right, so where are the Calabi-Yaus? Next thing we need to talk about is vacua. So I dodged writing down the action. But I told you at this very long introduction that to know what the vacua are, we need to look at the zeros of the scalar potential, just like we did in the Higgs example. So what we'll have to do is, if you are on your computers, you can look into Witten's paper and see that after a very long discussion about action and supersymmetry and many, many complicated terms, he reads off the interaction term for the scalar fields. And this is what we need to look at when we want to know what the vacuum is. And in this, I'm just writing down the result without giving the derivation. And if you look into Witten's paper, you will see why I'm not giving you the derivation, because it's actually really complicated. And let me just write this down and then comment on it. So I've introduced all the notation. So here, for instance, is this pairing with the gauge charges. I'm also suppressing indices I that are assumed to be summed over. So you see that this is, as it emerges, much more complicated than, here's some new notation I will introduce. It's much more complicated than your average Higgs potential. And really the structure of this potential is more or less governed by two-dimensional supersymmetry, that you have this result. So I haven't introduced a few things here. So the E is just the gauge coupling. We don't see the full complexified parameter T that I introduced before, but only the Fi parameter at the classical level. The theta angle actually only sneaks in at the quantum level. What I haven't introduced here, because it's abstract at this point and I'd rather be concrete in the example, is mu is a map from our space of fields into the dual Lie algebra that mathematicians call the moment map. And I will write down in examples explicitly what that is. It's more or less determined by the gauge charges and the way the fields transforms. And this expression here is typically called the D term, because it's related to the auxiliary field in the vector multiplet, which is usually a scalar denoted by D. And this is called an F term, because it's related to integrating out the auxiliary field in the chiral multiplet of the supersymmetry. So there are a few things to observe here. So our goal will be to find the zeros of this potential, because this will give us the vacuum. And there's a few things to notice here. At first, this is not a trivial task, because these are highly nonlinear terms. Second, and that's good news for us, each of this term is a square or a modulus squared. So it's positive definite. So if we want to find a zero, we have to set to zero each term individually. And that's still difficult to find the solutions for in a general context where you have many phi's and many sigmas and many q's, but it's at least possible. So U is a sum of squares. It has to be bounded from below because of physics reasons. And another thing to observe is that there are different types of solutions to U equals 0. And there I just want to do some name dropping, because this is something you read very often in the literature, and they have names like Higgs branch, Coulomb branch, etc. So we will have to add, there is a lot of analysis to be done to just understand the vacuum of this theory. And this is also really the connection to mathematics. A lot of the mathematics that comes out of string theory is actually just the mathematics of supersymmetric ground states. And this is also true in this context. So let me say a little bit more about how we can solve this, like on general grounds, and then we'll do the quintic and then we'll be done. Unless people have some questions about further reading, otherwise you will get that in the notes. All right, so let me talk about the Higgs branch first, because this is sort of a generic way to get this U of phi close to 0. And if you look at the first line here, this is the only terms where the sigma fields make an appearance. So one very intuitive thing to do will be to set all the sigmas to 0, and that already eliminates the first 3 terms, the whole first line. And this is actually what is really done on the Higgs branch. And then U equals 0 is determined by setting the last 2 terms to 0. U equals 0 is determined by mu of phi equals theta. Remember that there can be many phis and many thetas, so this is not the one variable thing. Finding the critical locus of our potential. And the first one is called a D term, and the second one is called an F term. And we still need to solve that, and you can have different solutions depending on what theta is. It's just a real parameter, and the solution space can change, as we will see. And the solutions actually made it to the title of Witten's paper, which are called phases of the GLSM. And they depend on theta. So very formally, we will find some configurations of the phis, hopefully, that satisfy these relations. So formally, we can find some manifold parametrized by these phis, by our scalar fields, and scalar fields make good coordinates. I mean, they have like all the properties that you want to have for a coordinate. Depending on which value of theta, is just formally solve this equation, and you have the group acting there you need to worry about, and intersecting it with the solution of dw of phi equals 0, which is written like that. And actually not quite obviously, you can rewrite the first solution to the first equation, and I will show you for the quintic how this works, as take the vector space, so the space of scalar fields, remove something that should hopefully ring a bell to something I mentioned half an hour ago, and mod out by the complexified version of your gauge group action, and well, keep doing what you're doing with your potential. So formally, things already look familiar, and this is called the deleted set. And it basically tells you that this first equation, which is still very abstract, need not necessarily always have a solution for all values of phi. And when it doesn't have a solution, you'll have to tell your vacuum will know that. And that already looks very close to a toric variety. And indeed, if G, the gauge group, is U1 to some power, this really reproduces the definition of a toric variety. And this is how the Calabi-Yaus comes in. So the geometry of your vacuum will be Calabi-Yaus with coordinates, the scalar fields. And this is really analogous to this Higgs example, where you have, well, the Higgs field is the one coordinate that parameterizes the circle, which is the ground state. So there's not a lot of magic to it. Again, just for completeness, I won't have time to go into detail. Another, and also not the most general. Oh, by the way, I should say this thing is called Higgs branch because typically there will be some spontaneous symmetry breaking happening. So the full gauge symmetry will not be there anymore. And because of that's the reason why it's called the Higgs branch. So similarly, we can go back to our complicated object and think about setting all the phi's to 0. And that actually does a lot. So you see from the second term here, that also means that classically you will have to set the fi parameter to 0 because this mu of phi will typically not contain a constant term. So if you set all phi's to 0, you will also have to set zeta to 0. The potential also have some mild condition that it's a real interaction term and not a mass term or a constant term. So this will typically also still depend on the phi's. And when you set this, when you set the phi's to 0, these last two lines are gone. This is gone. This is gone, and the only thing that's left is this one. But if you're already having like a commuting gauge group, for instance, this is also not a constraint. So basically, what you find when you set all the phi's to 0, that this can only be somewhere in the parameter space, at some point in the parameter space, where the zeta is 0 classically, and get some quantum corrections later. And the sigmas have to commute, which is a constraint in the non-abelian case, but no constraint in the abelian case. So basically, the sigmas are not constrained anymore. So phi equals 0, theta's 0, and sigma theta unconstrained. Classically. And typically, that's not something that we want to have for a good ground state of a theory. We don't want our field to be able to take any values at the vacuum. This is a really bad thing. Luckily for us, this theory is saved by quantum corrections. And this comes back to a question I had previously. Why do we only have the ground states? Don't we do anything with else? We can fully quantize this and we can like do one loop corrections and stuff like this. And in the context of the Coulomb branch, we actually have to do it to see that the theory makes sense after all. So saved by quantum corrections. And because it's so supersymmetric, the only perturbative corrections you have is one loop corrections. And Witten computes them explicitly with classic methods of quantum field theory in his papers, which give a potential for the sigmas. And it's called the Coulomb branch because already this first term here tells you that whatever gauge symmetry you have is broken to a U1 symmetry, because only then the sigmas who are Lie algebra values will commute. And so you have like a U1 theory there that's like describing Coulomb type interactions. And that's where the name Coulomb branch is coming from. All right, so in general, when you have more than one zeta, so higher rank gauge groups, you have a lot more freedom, you have a lot more parameters, you can have mixed Coulomb and Higgs branches, and these are typically very difficult to analyze. As I won't have much time, when you have a non-abelian gauge group, another thing that can happen is that the symmetry is only broken to a continuous subgroup. Then your ground state will be associated, will not have like a fully broken symmetry group, but will have still be see the non-abelian symmetry group, which is like a confining phase basically of the theory. There is sort of, yeah, this is still work in progress, I would say, to fully understand this like non-abelian GLSMs. All right, since time is running, I think I should now put all the ends together and do the quintic. So what I'm going to do now is I'm going to do the prototypical example and see how this works out. And the goal will be that if I choose a specific choice of gauge symmetry, field content, and type of symmetry transformation, my ground state on the Higgs branch will actually be the quintic threefold, as I just introduced them before. So let's do that. How do we find the Calabi-Yaus? Okay, I'll just go through the data as I introduced it before. So we will use the simplest gauge group imaginable, which is a U1. And then the field content is already quite a bit complicated, but it's not a surprise because I just said that the scalar fields correspond in the end to coordinates of the manifold. So as we had the definition of the quintic before, I should introduce at least 5 complex variables, which means 5 chiral multiplets with 5 scalar components. And sort of the ingenious idea by Witten was that everything becomes nicer if I introduce an additional field, complex field, which is different than the other 5, which is typically denoted by P. So my vector space is going to be a complex space for the P field plus 5 copies of a complex space for the X fields. And typically one writes how they transform under the gauge transformation here in parentheses. So this will be 1. So in other words, the gauge charges associated to the phi's will be -5 for the P field, 1, 1, 1, 1, 1 for the X fields. So that just means that x1 goes to lambda to the 1, x1. Here comes the scaling relation again, where lambda equal is in U1 or C star, and P is lambda to the -5 P, and so on and so forth. That's what I mean. And you observe that sum over I of all the charges is equal to 0. -5 plus 5 times 1 is equal to 0. And that is the concrete realization of the statement that U1, that the matter representation is an SL representation. Means that the weights sum off to 0, and that already tells us that we will have to deal with the Calabi-Yaus. And if you choose, for instance, a GLSM, which does not satisfy this condition on the charges, it's still perfectly fine. It just describes a manifold which is not Calabi-Yaus. But you can still do that. All right, I also had the R charges. They will not really play a role in the rest of the talk. All I need to know is that there will be a potential that will have R charge 2, and we will see once I write this down that this is a consistent choice of R charges. There is, because we only have a U1 gauge field, there is one Fi theta parameter. There is one sigma field, which lives in the complexified Lie algebra of U1, which is the same as U1 itself. So that's practical. There is a potential. So what we'll have to do now is we have our field content, and we will have to write down the most general interaction term that is gauge for this field that is gauge invariant and has R charge 2. And because I have given the P field R charge 2, it had better appear linearly because that already carries the full R charges because I've given the axis R charge 0. And that has gauge charge -5. So we'll have to multiply this with something that has gauge charge +5, which is, as we've seen before, a generic any degree 5 polynomial in these 5 variables. So the quintic already wants to make an appearance and the conditions are satisfied. So next thing to do is to write down the scalar potential explicitly. So going back to the most general form, we see here that we only have one sigma that trivially commutes with itself. So the first term here is already gone. And we have to sort of fill in the gauge charges for the various fields for the second term here and the D term and the F term. So that's fairly easy. So the first term is standard. So we'll have to take the modulus of the gauge charge of the first field multiplied with the sigma times the P. And then we'll have all the X contributions. And I said before that I suppressed a lot of sums over the fields and now I'm introducing them. And then plus sigma is exchanged with sigma bar. And then we have the D term, so there's only one gauge coupling. It's a Yuan theory. That's why I call the coupling E. And the moment map that I haven't given before, the recipe for Yuan gauge theory is take the charge and multiply it with the modulus squared of the field. So we do that for the P field, and then the X fields are as they usually are. So we have 1 times X squared, and we subtract from it the Fi parameter, and then we have a dW squared. All right, so we have to set this thing to 0. I will not talk about the Coulomb branch, but let me talk about the Higgs branch. So we have sigma equals 0, kills the first line, and the second line becomes, we have to solve -5 p squared plus sum I equals 1 to 5, xi squared equals zeta. Zeta is a real parameter, remember. And then for the critical locus of W, we have to solve, well, the P derivative gives us one equation, namely the degree 5 polynomial has to be 0, and then the X derivatives give us 5 more equations, like this. So this is the set of equations that we have to solve. The D term, one D term equation and 6 F term equations. And actually, I wasn't quite honest with you. We will make some mild assumption on the genericity of G5. So the assumption, and that will actually ensure that our Calabi-Yaus is smooth, is that the only solution of dg5 dxi equals 0 is x1 equals all of the x's equals 0. That's an assumption we will make. That just means that the G5 has to be suitable generic. All right, and now we can actually solve these equations, and you will see that it will depend on the sign of this real parameter zeta, on the Fi parameter. So, and that will give us the phases of the GLSM. So the way we do that is, and I actually might make it on time, if we have zeta larger than 0, so we will have to distinguish 2 cases if we look at the first equation. So if zeta is larger than 0, for this to have a solution, we have to make sure that at least one of the x's is non-zero. Because if one of the x's is 0, then this then the right-hand side will be positive and the left-hand side will be negative. So this is the first observation. So no solution for x1 equals x5 equals 0. And this will be this deleted set. And that's already a good sign, because that also was part of the definition of the projective space that we had in the definition, in the mathematical definition of the quantic I gave you. So the physics already gives us something. And then if we take into account, if you look at the third equation here and take into account these assumptions, we will see that we only find a solution if we set this nasty variable p that we wouldn't expect for the quantic to appear to 0. And then if we do that, the only thing that's left is G5 of xi equals 0. Here's our hypersurface. And furthermore, even though the gauge symmetry is broken, we still have a scaling symmetry, which still persists. And this is all we had to do. So we'll now have in the parameter space zeta larger than 0, we found that we have to look at x1 to x5 and what's the space? It's C5 minus x1 to x5 equals 0 modulo the xi scale, which is exactly complex P4 And that really came out of the solutions to the vacuum equations. And then G5 of xi is equal to 0. So we have discovered the quintic as the ground state of a supersymmetric gauge theory, and we only needed to look at the scalars. So this was sort of the main message I wanted to bring across in this talk. The Calabi-Yaus is a vacuum equation of the gauge linear sigma model. But that's not the whole story. So in my last 7 minutes or so, let me just say about the question I had with the nonlinear sigma model. So what we have now is a vacuum. But what we can do now is we can look at small fluctuations of all the fields that are set to 0, in particular the fermions, expand the theory around the vacuum and find out what the low energy effective theory is. And it turns out, actually, if you do this analysis, that the low energy effective theory is precisely this nonlinear sigma model that I mentioned before. It is sort of a theory that maps a Riemann surface into a Calabi-Yaus. You can write down an action, it's a superconformal theory. So since I had this question, maybe let me write that down. So the low energy effective theory so you go beyond the vacuum with standard quantum field theory, fluctuations around the vacuum, is this nonlinear sigma model that I mentioned before. So you find a conformal field theory in the IR of the GLSM. And the action is what I sketched, and the target is the Calabi-Yaus itself. All right, so last thing I want to stress is what happens if we make this parameter negative. So this is not something that we would usually expect. We have a Calabi-Yaus, zeta is a volume parameter. Zeta more or less describes the volume of the P4. From this geometric perspective, it doesn't really make a lot of sense to set zeta to a negative number. But we can do it in the GLSM, it's just a free parameter. And the solution actually looks kind of boring. So we still have sigma equals to 0 as everywhere on the Higgs branch. If zeta is less than 0, then we are not allowed to set the P field anymore, to 0 anymore. So the solution will change, but we can set all the x's to 0. So what we will find is that we have xi equals to 0. So all our Calabi-Yaus coordinates are gone. And all we left is we have no solution for p equals 0. That means no geometry at all, and it turns actually out that x zeta 0, just the classical analysis, or just the vacuum, is a point. And that's just given by this. Remember that zeta is negative, so minus zeta is positive. And that's kind of not a Calabi-Yaus at all. And this is also not the whole story. So what you can do again is you have now a point-like vacuum as in scalar to the fourth theory. You can expand around this vacuum by turning on small fluctuations of the axis and see what kind of low energy effective theory you get. And the point is that so the low energy effective theory turns out to be something that's called a 2,2 Landau-Ginzburg orbifold. So what does that mean? So P gets a VEV, a vacuum expectation value, namely the one here. But we can turn on fluctuations of the axis. And because of this VEV and the way this quintic potential looks like, or this interaction potential, is that the U1 gauge symmetry we had before is broken to Z5. So spontaneous symmetry breaking is happening, but only to a Z5 subgroup. And the theory is take the x's, which are now the small fluctuations around the vacuum that we turned on, that lives still in 5-dimensional complex space, but we have this, there is a singularity in there because we have this Z5 action, and that's why it's called an orbifold. And this is not something geometric, and that's what I meant in the beginning with there is different mathematics in different sectors of the theory. So algebraic geometry will have to be generalized in this kind of singular settings. And we also get reintroduced the potential, which is the vacuum expectation value of P, and then the potential given by the small fluctuations. That more or less by definition is a Landau-Ginzburg model. And maybe you'll have other talks talking about Landau-Ginzburg models. And this is how I want to end, this is the famous Landau-Ginzburg Calabi-Yaus correspondence. And this was also the main reason why Witten invented the GLSM, because in the late 80s, people have studied Landau-Ginzburg models, and they've studied Calabi-Yaus, and they computed spectra and all kinds of physics, and they realized that the Landau-Ginzburg model and the Calabi-Yaus somehow behaved very similarly. And what Witten did with his GLSM is he basically showed, okay, they're just two low energy configuration of the same parent theory in the UV. And this is what I just showed you. And since my time is up, I will stop here. Just to let you know that this is really the status here. We're now at 1993. And I will send Daniel the notes. I will have one more page of, just a list of bullet points of things that go beyond that. And you're very welcome to look at those papers. And I hope that this talk somehow gave you an idea sort of about the formalism and about the idea that GLSMs, that if you want to read those more modern papers, you will not be completely lost. So thank you very much for your attention.
And thank you very much for the wonderful talk.